Welcome back to Ask a Creationist. I am Todd Wood. I'm president of Core Academy of Science, and I am a young age creationist, and I am here to answer whatever questions you want to throw at me. Hopefully something short and simple that I can do quickly. This week we got a complicated question, though. Comes from a viewer. A lot of creationist ID proponents seem to attack the evolutionary mechanism of natural selection plus random mutations. But what about other evolutionary mechanisms? And this person specifically wanted to know, how does that relate to our understanding of created kinds? Good question. So I thought maybe we could start with a little timeline here, have a little review of what we're talking about. So let's begin in, say, 1836 here with the return of the Beagle to England with Charles Darwin. He had aboard there some of his specimens, all of his notebooks. He'd sent a lot of specimens home already to England. Very shortly after that, within 6 months, he's written down that he's essentially convinced that species originate from other species. Now, no, this is before he's figured out how that happens. He's just decided this is what happens. 18 months later, September of 1838, Darwin is reading a book by a guy named Malthus, who is making some rather startling, by our modern terms, arguments about populations. His attitude is essentially that poverty is kind of good because the poor are unfit to survive, they die off, and the rich, the ones who are capable of getting money, they're the ones who should be, leaving offspring and so forth. They're the ones that are successful. So poverty's good, in a sense. Darwin gets this idea of natural selection by reading Malthus, that in sort of the struggle for limited resources in the world, the creatures that are better able to obtain resources are the ones that are likely to leave offspring. Years later, 20 years later, 1859, his ideas appear in what he calls a short, abstract form, The Origin of Species. Kind of a funny name because it's a really long book. He had a much, much longer thing planned, so I'm kind of grateful that he's only produced this short thing. Now, you would think that that would lead to acceptance of his ideas and that the world was all different. But actually, that kicked off a good 80 years of debate over natural selection. People, by, say, 1875, I would say, the scientist types had sort of agreed that evolution happened. That's where we get our species. But they did not agree how it happened. And it would take a revolution in genetics, population theory, natural selection, etc., to sort of explain this mechanism. And this was termed the modern synthesis. So that's where we get the idea of natural selection. In a nutshell, what is it? How does this work? Well, various ways of thinking about it, sort of the most technical ways. Different versions of genes, alleles, have different rates of survival. And over time, the fractions of alleles in a population changes. And this produces what we think of as adaptation. Now, how does this relate to the change of species? Well, that depends on what the variations are, right? And that's where the random part of random mutation comes in, because the mutations could be almost anything, and they could change almost any character. Things could adapt to any open environment. It just depends. And of course, I don't want to pretend like this is the whole thing of natural selection. I could teach a whole course on natural selection, biological change, and I don't have time for that in this short little video. So understand that I understand there's more to it than just this. There's a lot more to it than just this. But that is sort of natural selection in a nutshell. Put it really simply, why is it that cheetahs are really fast? Because if they weren't fast, they wouldn't catch prey, they wouldn't survive as well, and so forth. So cheetahs end up being fast. It is kind of a logical thing. Why are things so well adapted to their environment? Well, because if they weren't so well adapted to their environment, they wouldn't survive, and we wouldn't be here to wonder about it. Interesting. Now, the modern world has brought us the science of genomics, advancing the science of genetics dramatically over what was known at the time of the development of the modern synthesis. And what we've come to understand is that, well, it's even more complicated than we thought. And I don't think any of this really negates the importance of natural selection or any one of the mechanisms. It's just emphasized to us that there's a lot more going on than just simple allelic changes and variations in a population. Now, what does this have to do with created kinds? Well, one approach might say This is how biological change happens, and that means created kinds must be these things over here, because we know we can't develop, we can't evolve that much variation, so it has to be this. This is sort of a deductive route, right? You could sort of say this is what we know about change, and this is how far it can go. Cool. My approach is a little different. I want to try to define created kinds based on as much evidence as I can. So I want to look at the fossil record. I want to look at morphology and anatomy. I want to look at genetics. I want to look at everything that I can think of and sort of try to inductively conclude what is or is not a created kind. Now, I'm not saying that any of these approaches are better or worse. They have their disadvantages, of course. I do, however, think the deductive approach tends to be a little too focused on mechanism. But ultimately, I see us at the very beginning of understanding how populations can or do change. I think we're just now sort of starting to explore this with modern technology and applying it into created kinds. Well, we could come up with some surprises, and I think we will. So let me give you an example. Here's a Dachshund, right? Good old Dachshund with their tiny little short stumpy legs, much shorter than they should have for the body size. And they're actually caused by something called a retrogene. And a retrogene, this is kind of mind-boggling. This is way beyond simple point mutation, let's put it that way. So a retrogene happens when you have a regular messenger RNA that's retrotranscribed by a reverse transcriptase, turned into DNA, and that DNA is reintegrated somewhere in the chromosome. If you don't understand what I just said, that's cool. That just shows you it's way more complicated than we thought, right? So you get this complicated stuff that changes the appearance of these dogs and makes their legs little stumpy things. And what's surprising is it's not happened just once. There's at least two of these things, one on chromosome 18 and one on dog chromosome 12. Different breeds of dogs have different frequencies of these different chromosomal variations, and they're not the same. Even though they are the same. They're a retrogene of the same sort of gene, but they're in different places and caused by different events. And you might be thinking, well, that's not natural selection. That has nothing to do with changing allele frequencies. Well, actually, it sort of does, because this producing of retrogenes is a way to change allele frequencies apart from natural selection. And this is kind of what I'm talking about here with these new ideas about how populations can change. It's not always just natural selection, even though natural selection is an important thing. So that's all I have for that question. I'm sure you have follow-up questions. Some of you might even be thinking, you should just do that course on natural selection you talked about. Yeah, thanks. Maybe I'll get to that someday. If you've enjoyed this video, check us out at coursei.org. We'd love a donation. Hit subscribe, hit the bell to get notifications if you like. You'll find links to our social media, Instagram, Twitter, and Facebook on our website. Thanks for watching. Send in your questions if you got them. Thank you very much.